Alright, this is 3.4. We're looking at transformations of cubic and quartic functions. I'm not going to take a very long time doing this lesson just because it is quite a big review from last year and transformations in general. So you guys should know how to do it. There's no real kind of tricks or I don't know, there's no kind of curveballs to this. It's just the same transformation methods you've done with regular quadratic functions. Now we're just translating them over to cubic and quartic functions. Okay, so it says the graphs of a parent function y equals x cubed and a second function, which is transformation of the parent function, are shown. So that's shown here. Okay, the blue is x cubed, and here's the transformed function. Okay, so right away, even before we start this lesson, this should kind of make sense to you, right? Because we've moved up 1 from the origin. You can, if you think of 0, 0 as a critical point where that evening out is occurring in the graph, you can see it's moved up 1, and you can see it's moved to the left 2. So we already noticed that right away, that there's +1 here and +2. We know we go the opposite direction for the x coordinate. And then we know that there's a negative sign, so it's flipped. You can see it has flipped, so it was going up on the right before, and now it's going down. Okay, and finally the last part is there's a vertical compression here happening of 0.25. So we have this sort of action happening, pressing down, so the y values are less for the same x values. Okay, so even before we start this lesson, you know, we already see kind of an end product of it and recognize all of the different transformations that are occurring. Okay, so we're not going to spend too long doing this. It says use dynamic geometry software to create a Cartesian grid with an XY axis. Okay, it's very important now. We're getting into more and more complex graphs that you do find an app. Okay, I know I've said it before, but it's important that you do now figure out which app you're going to use so you can make these graphs. Okay, I have this one called Algeo. And you can just punch in whatever you want. There's a graph, and then you go to draw, and you can zoom in and out. Okay, and then I can do another graph on here, x squared, 2x squared, okay. And it draws the graph. Okay, so you want to get a graphing app that does that for you. Okay, it'll be really helpful, especially in this section. Okay, so it says the first step is to plot x to the exponent of 3. We know what that graph looks like now. Here it is. Next it says define 4 new parameters, 1, 1, 1, and c equals 0. So we're not doing much to the graph here if all of our translation variables are 1. Alright, so here's our graph, our equation with all of our variables in it. Okay, again, nothing new here. This should be really familiar to you guys. We've seen this many times before last year. Okay, we're using the same variables. A to dictate the vertical stretch or compression, K to dictate the horizontal, D to dictate the horizontal translation, left or right, and C, the vertical translation, up or down. Any questions about that?
What was the Chrome extension app called for graphing calculator?
TK graph. Yeah. Describe how the new graph g at x is related to the graph of the parent function. So there's the new graph here. You can kind of read these variables here, 1, 1, 1, and 0. So c is 0. Everything else is 1. And so there's a horizontal translation happening of 1 unit to the right. Okay, because it's going to be -1 up here. Right? The equation for our new graph with these variables would be h at x equals a is 1, so we don't put it, k is 1, so we don't put it, x minus 1 cubed, and c is 0. So there's our equation for the graph, and there it is in orange over here. Okay, so the only thing that's happening with these variables is that we're getting a horizontal translation of 1 to the right. Everybody okay with this so far? I've gone very quickly, but the idea is that you guys have already seen this. So you're good with this, everybody? Nobody's really lost? Okay. So then it just says, there's a bunch of different examples it gives, and it says change the different values and see what happens. Well, we know what's going to happen. What if I change the a value here to 5? What's going to happen to the graph? Yeah, there's going to be a vertical stretch, so it's going to go up much quicker and down much quicker like that. Okay? Yeah, it's going to get skinnier. Likewise, if I change the a value to a fraction, so less than 1, there's going to be a compression happening. Okay? If I change the value of c up or down, it's going to move the whole entire graph, translate it up and translate it down. Any questions? Okay, again, I'm going very quickly. Same idea with x to the exponent of 4. We should know what that base graph looks like now, right? We should all know this. Okay, this is y equals x to the 4. Okay, now if we have translations to this graph, we have plus 1, it's going to move up plus 1. Okay, and then horizontal, vertical compressions, etc. Describe the transformations that must be applied to the graph of the function x cubed to create the graph of y equals a k x minus d to the exponent of 3 plus c. So there has to be a vertical stretch or compression of a, horizontal stretch or compression of k, a horizontal translation or movement to the left or right of the value of d, and a vertical movement of c. Same thing for the even function. Or sorry, the function with an even exponent, I should say. Do you think your descriptions in part I and j can be applied to transformations of the function x to the exponent of n for all possible values of n? Explain. What do you guys think? Yeah, probably, right? It's worked for every other function we've ever tried, so it's going to work for all functions with any exponent of n. All right, the examples should help explain. Use reasoning to determine the transformations. Describe the transformations that must be applied to y equals x cubed to graph this, and then graph this function. So, the first thing I want to point out, be very, very careful, because a lot of you guys messed this up on the first quiz. Notice how the coefficient of x is not factored out. You see that, Philip? What do you have to do? David was maybe the only one in the class that did it in the first quiz. You remember what he did, Philip? What do I got to do with that before I start with my transformations? Yeah, how do I do that?
You just we have to take out the brackets, but
Take off the brackets?
take it out the brackets.
No. I want to add brackets, if anything. So it's tricky, right? Because it doesn't really look like it's common, so how are you going to factor that out? Luigi, do you remember?
Would you divide by a half?
Yes. So you take a half, and now you divide both terms by a half. So you're left with, Philip, what's 1/2 x divided by half? X, good. And then plus, no, 1 divided by, good. So I showed this after the first quiz. There's only 2 guys who did it. Be very, very careful of this, because it's very tempting to say that there's a horizontal stretch of 2 happening here. Okay, and there actually is a horizontal stretch because we factor the half out, so there is a horizontal stretch happening of 2, but you'll get the horizontal translation wrong if you don't factor it out. Okay? And then the -3 stays on the end. Any questions? There. That's the one trick. Yeah.
So this is only for a cube graph?
No, it's for any graph. It doesn't matter what this exponent would be. You'd still have to factor that out. Because you need to put it into this form, right? You need to have the graph into this form. Okay, right here. Before we can start doing the translations. Okay? And the way we had it before, we didn't have k on the outside of the horizontal translation d. Any other questions with that? All right. So you'll notice that's the first thing they do. It says factor the coefficient of x so that the function is in the new form. They want it to look like that. So until we factor out k and have x plus d in brackets there, we don't have it in this form. So next, the other stuff is pretty straightforward. It's vertically stretched by a factor of 8 and reflected in the x-axis. That's because of our negative sign. Horizontally stretched by a factor of 2. Remember, for the horizontal stretch or compression, it's the inverse of the k value. Okay, so if it's a fraction, it's actually a stretch. And if it's a whole number, it's actually a compression. You guys remember that? Okay. Translated 2 units to the left, so +2. Again, it goes opposite direction for the x value. And then translated 3 units down. Okay? So the book always does this kind of table of values method. I don't particularly like this, but I'm going to explain it anyways. This is what they do. So they do the parent function. They find their values. Sorry. Okay. They do the parent function. They find their values for just x cubed. And then they do kind of each step individually. So here they're doing the stretch and the compression. So they're multiplying by -8 the y values, and they're multiplying their x values by -2. Sorry, they're multiplying their x values by 2 and their y values by -8. Any questions what they're doing here? And then they're graphing one step at a time. You might want to just go from the graph and move everything at once. Next thing they do is they do their horizontal and vertical translations. So 2 units to the left and 3 units down. So they're subtracting 2 from the x value and 3 from the y value. And they end up with this blue graph here. Okay? If we go back to the original equation here now. So here's the equation once we factored out that half. There's our equation. And there's our graph in blue. Let's see if it makes sense. So we take the original graph, which is in green. We're going to first apply the vertical and horizontal compressions, or vertical or horizontal stretches. So we stretch by a factor of 8, so it's getting much skinnier. We reflect in the x-axis. So it becomes this red graph now. And then we just translate it 3 down and 2 to the left. So you can see right from the graph, the equation relates very easily to the graph. Okay? So here is just a different method. They combine the vertical and the horizontal stretch first before doing any translations. And look, they find out that it's -1. So that's why the final graph doesn't look much different in terms of its stretch, because they actually cancel. The horizontal and vertical stretch cancel. So you definitely can do this. Just be careful when you do this that you apply the cube to the half before you bring it out of that brackets. Do you see that? it's 1/2 cubed. So this becomes 1 over 8 times 8 is just 1. So -1 there. Any questions what they did? And then they apply just the horizontal and vertical translations and the reflection, and they're done. Okay? Sorry, that's also a point I should have mentioned here. That's why the red graph here doesn't look stretched or compressed compared to the green. Do you see that? Because the 8 and the half cancel. Right? The half cubed, they cancel to give -1, so it just looks reflected. Okay? So always a good idea to simplify. You're always going to make your job easier. And then they just finished the table of values to do the graph. Number 2. Determine the x-intercept of the function. So x-intercept, what do we have to do when we're looking for the x-intercept? Yeah, Jesse. Yes, first step is we're going to say y equals 0. Okay, so we do that over here, y equals 0. Now we're going to rearrange and solve. So the 48 comes over to the other side, becomes positive. Divide by 3 because there's a 3 here. So we get 16 is equal to this. Some of you might stop there and be like, I don't know how to solve for that x. You need to take the 4th root. Okay, to get rid of that 4th exponent, you need to take the 4th root. Because it's an even root here, we have to use plus or minus. Okay, because -2 or +2 multiplied by themselves 4 times will equal +16. So that's why we have plus or minus 2 there. So then we need to consider both cases, +2 and -2. And so we end up with our x-intercepts of -4 and -8. Any questions? So we have our zeros already. Okay, this is the same solution. They just used a graphing calculator. Not needed. Could have used the algebra just as well. And that's it. The last part. In summary, our polynomial function looks like this, can be graphed by applying transformations to the graph of the parent function. So notice how they've replaced the cube and the 4th exponent by n now. And they're saying where n is any integer, so this transformation method applies to any exponent. Okay? Any function raised to any exponent. So quartic, quintic, all of those functions can be transformed in the same method. And then it says each point on the graph of the parent function changes to x over k plus d ay plus c. So this is good to have. Okay, rather than doing all those tables that the book has, if you just remember this, you can transform any point into the new point using that formula. All right? Any questions about what this means? You're just taking the x values, you're applying the compression or the stretch, as well as the horizontal translation, likewise for the y values. When using transformations of graph functions in fewer steps, you can apply a and k together and then c and d together. So you're actually canceling out a and k by multiplying them. Need to know the value of a represents a vertical stretch, value of k horizontal stretch, d horizontal translation, and c vertical translation. This is all review. Any questions?